Hello everyone, here our second episode about physics-informed neural networks. Here we take a famous examples from PINNs and we dive deeper into what are PINNs useful for, how to use them in a practical example, and some key open research questions about them. Towards the end, we dive deeper into how to think of validation and the importance of spatial discretization in the context of PINNs. If you already know our example and are just here for the deeper dive, I leave the timestamp in the description, along with some useful resources. Thank you so much for the fantastic reception of the first episode, and I hope you enjoyed this one as much. Okay, so welcome to the second episode of Let's Put a Pin on It. In the first episode, we talked together about what pins actually are, and we went through a basic understanding of it and how they change the normal role between data and equations in neural networks. So how they allow neural networks to start considering equations and all that is packed inside. You had a great idea that is maybe let's not keep talking too much in general about pins, but let's bring some good examples of what a pin could look like. And you have a quite extensive literature review, and so you cherry picked a couple of examples that can help us going a little bit forward into understanding all the little details of how this technology works. So I think I'll let you go with presenting it. Yeah.
All right, thank you, Gabriele, for having me again, and thank you for I think it's a great idea. We are having this series here. Let's see how it goes. But first episode was very exciting. Actually, I really enjoyed it,
and I'm super excited of exactly of trying to challenge everything, and then you ending up on top. Yeah,
exactly. Hope so. Well, no, but it was I really like the way we ended, like the last episode. Like your question about okay, well, what if someone is just like getting interested in pins, how can it learn? How can they engage and become expert in it? So, and I think so for today I would like to kind of like guide you and all our people that's gonna listen how like my thought of process, okay, how you go from let's say a simple data regression, so a classic data regression task, to what it is like a pin with all the features that the pin framework can have. So of course, just to start from Adam and Eva, we all know what data regression is. Okay, but just a quick remark. Okay, we gave an input-output. Let's say the most common one is the linear regression. So we approximate E with a linear equation and a linear function, and then our parameters are the slope and the intersection. Of course, when things get a little bit more complicated, let's say the data are not that linear, or there's something weird going on, we can record there are many options. Of course, now one of the one that is especially with these AI waves coming, neural networks. Oh my God, neural networks so awesome. They can learn everything. And to a certain extent, it's true. They are universal approximator. Whether architecture you use, whether it's a simple deep learning, or we go something more complicated, or then there is also what they're called extreme learning machines. That is something that we should definitely dive
and
into.
indeed to, let's say, explain for people that even though probably our listeners all are aware of the learning part on a linear regression, is really learning the parameters of that function that best approximate your data. So that's the learning component, and there is the assumption of the function is going to be like this. On neural networks, I think we are working with something similar, but still often when you start drawing neural network that are a little bit complex, you kind of give up the details approximation of how the function would look like, because here we are looking about a lot of sigmoid function of weights and biases that are, let's say, nested in within each other. So I think when you open that door, you soon lose the, okay, that's how I assume my function will be, and you start talking a little bit more in abstract on which kind of operation is my set of layers likely to well convey. And so the learning part stays into adapting weights and biases of your neurons, but indeed, as you're saying, as universal approximation is you're trying to create structure that can approximate arbitrarily complex underlying functions. So like in the linear regression, right, that you have to say, okay, I assume is simple. A way for somebody to start on neural network, I think, I assume the function is complicated, right? And instead of simple, and then I move on from there with the same learning aspect. Yeah.
No, yeah, exactly. And also, no, and to what you say, I mean, you said it perfectly. I completely agree with your statement. And also, that's what makes, in my view, like neural networks beautiful and terrible at the same time, because that's the what gives them, like, the black box. You get input output, but you don't really know what's going on in people start, but how can and of course, I mean, your neural network are a subset of AI, a really big subset of AI, let me put it that way. And of course, people then, when you go to application, especially if we're talking about engineering application, they say, yeah, but how can you make AI algorithm, neural networks, whatever, trustworthy? And maybe we'll see that PINN can be something, toward a big step toward that direction. Maybe not the only one, but definitely for certain application, especially for what concern scientific application. I think PINN can be a good ingredient.
Build towards more trustworthy. So this big field of trustworthy AI that, again, like many things in AI, means very different things to very different people. But even like AI itself, I have to say, because if you ask 10 people what AI is, there you will probably get 10 different answers. And I think one of the great examples is what you said. Is I totally agree that neural networks are a subset of AI, and let's say large language models are a subset of neural networks, right? So you go in the smaller set, but I guess most people right now, when they refer to AI, they refer to large language models, and everything else is different. But that's something that I think it's important to have a conversation about it, because with how rapidly the field is evolving, we often lose definition in the way, and then we end up talking about completely different things.
No, definitely. You got a great point. That's why also when you will hear me speaking, I always kind of like stress, maybe I'm going to repeat myself a lot of time, which kind of like looks awful. But even in my papers, if you read my papers, are so simple, like, I write a sentence like subject, verb and object, and I always repeat it because I want to make it clear. Yeah. And funny thing,
and I think it's fundamental, because otherwise you get really lost in we are talking about things that we call with the same name, but they're different aspects.
We're not we're not trying to rewrite any Divina Commedia, so we need to be clear. At the end, we are scientists here. Oh yeah, but to connect with these all black box things, whatever, you try to do data regression with any framework, but let's stick on neural network. Of course, there the issue is, okay, as long as you have data and you train within your data range, that's fine. Okay, especially if the data are okay, you're fine. You learn it. We have tons of different examples that we have. One of the most classical one is the damper, the spring damper, and there you have, as long as you have data. Let's say we want to simulate. We collect position, time, and position, and we want to see where our little balls is. So going to the position of the damper is. And that's the most classic.
Indeed, and that's a great work. I never remember the name of it, but I think we will figure it out and put it down there somewhere. But indeed, a great introduction to PINN. So let's look at an harmonic oscillator of which we actually know the solution.
Exactly, go from there. And that I think the work is the guy who made that work. The great example that I really like it is, I think it's Ben Mosley, Dr. Ben Mosley. I think it's from ET. Is the age in Zurich? I think so. Something we can check better, but I think I'm not that far. And so kudos to Ben to pull this great example, and actually the example where we connected back again and start talking to each other and starting doing all of these.
It was a post of the post about this.
Exactly. But no, yeah, in that example you clearly see, okay, as long as I have the data, I can, no matter which kind of neural networks I plug in there, probably you don't need a very complex one. You learn everything. Okay, good. Then when you start having issue when either you have not enough data, or the data are scarce, or the data are not that accurate, and or both the scenario. And indeed, if you recall, that in that example, it shows exactly the point where, okay, I think in his example is like when you don't have enough, at some point you stop having the data. But then the same is when the data are scarce.
Yeah, it does just the first oscillation, right? So
Exactly.
the damper, it gets the first two rounds,
Exactly.
and then clearly the network, let's say the database network, not a PIN, doesn't have enough data to understand that these things will continue, but it thinks there is a single damping because what he has seen in the past is just one damping, and so he said, okay, this is going to continue. Yeah.
Exactly. And then, whether because maybe there the network should try to extrapolate because you don't have enough data, and we all know how extrapolation is very hard to do with all these
for networks, but also for humans. Yeah, absolutely.
Exactly. I mean, if we are that good to doing extrapolation, probably many of us would win lottery, and so we
indeed.
never know,
and what I think I really like about this example is that it clearly shows one of the problems that applied machine learning has every day, right? Because on the theory and on the more academical side of machine learning, often people work with extremely complete data sets, and they try fancier and fancier algorithms to get better at the job of understanding the patterns that you can see in data. But what you actually see when you start applying in real case scenarios, 9 times out of 10, you're not limited by your computational power of running a complex algorithm. What you're limited about is the data, right? And what he says is, I think, really echoes something that could happen, or meaning, okay, maybe you even have good quality data, but it was too expensive to gather it, so you just did the first round of it, and
Exactly.
clearly you're asking too much to your network to get something out of it, right? And I like the example you got, because here you see as okay, but if I think about the physics, actually the physics is not that complicated, right? So can't I put physics backs inside my network?
Yeah, to get back, you made a great point there, and I totally agree. And also to complete what you said, there is also the issue is to, let's say we can collect all the data that we need. The data are great accuracy, but then we also need to be careful on then do not overfit the data. Because then, there is also that issue, maybe if you stress too much about the data, depend on the problem, and especially like a physical problem, if you stress too much about the data, maybe, okay, you can learn exactly what's going on in the data, you can have enough data to cover, let's say, all your domain, but then maybe you then overfit, and that's another issue.
And this actually brings me to another question that I had for you, because I think that's a bullseye on something that actually I would like to learn more about PINNs, because as you see in this example that you brought, let's say you have partial data. The neural network cannot do the job with just the data, but if you show him and let's say add to this loss function that contribution we saw last time that comes from does it satisfies my equation or not, then you can go back and have a really good solution. And this looks really brilliant, but really added the connection point between classical equation-based systems and let's say database system. But then it opens a question for me, that is validation. You were talking about overfitting, and this is part of what traditional machine learning does validation for, right? To avoid issues in which you extract too much patterns in your test data that are not general patterns, but just things that you see in your trained data. Sorry. And so if I think about validation from the two camps, so the classical equation-based system, and I'm talking about our finite element method, so the old way, not your way, but the old way of solving equations, and a classical machine learning, so database system without equations, right? Both of them talk about validation, but I think the two of them talk about two quite different things when they talk about validation, because if you are on the finite element system, so you have your PDEs and you basically don't want to rely on data at all, the main idea is that given that you use the right physics, and your right physics is your system of equations, you have the right boundary condition, right? Then you have theorem that ensure you that if you find a solution to that PDEs and that boundary condition, right, that is the only possible solution. So you found the solution of your system. And so you don't have to question yourself about too much of this intrinsic, let's say, accuracy of your solution. You just have to check that you indeed got it. So validation there is something that in practice needs to be done, of course. But the spirit of validation in normal PDAs based, to me, was always, let's check that we haven't done huge mistakes, right? We didn't choose the wrong equations. We didn't put the completely wrong material models, but it's more a validation of the okay, let's run a couple of experiments and see what we predicted. Does it fit what we actually see in reality? But it's mostly we are sure that our solution is actually the solution to the physics. So it's a perfect solution apart from numerical approximation. And are we doing there, or we did huge mistakes? While when you talk about classical machine learning, so not PINNs, but just data-based method, the validation is really taking some different assumption. And I always see it as, okay, I have some data that will have some information, and did I manage to extract the right kind of information to my data? That's kind of what validation classically does. That is basically, I have my data, I take some part of the data out, and this data should be representative of the problem I will then want to apply my network to. And then I just train it on the rest of the data and see if my performance is what my training tell me should be, right? So you're talking about overfitting. That's one of the big checks that we need to do in validation. But what I want to achieve with validation in the two cases is quite different. One is, did I find the right one single solution? And the other case is simply, okay, is what my network tells me his accuracy is kind of reasonable? Because in the database approach, you have no pretension of finding the unique solution, right? You just find a minimum, and then you decide separately if this accuracy is good enough. But is not the job of the validation there. Yeah. And so this long thing opens to me the question: how do you look at that one in PINNs, right? Because as you showed last day, the PINNs have this dual nature of being potentially database and equation based at the same time, right? And then your validation, what are you trying to do? Are you trying to check, did I find the unique solution? Or did you find to check, okay, did I extract only the right things of the data, right? How do you evaluate the validation process there?
So that's a great question, great point. I mean, you touch, while I was listening to your question, a lot of interesting things to say came up to my mind. So yeah, in the PIN, so what we're trying to do there is trying to evaluate the generalization error, which of course is the difference between your real solution and your approximation that you don't know. Because if we did know that, we would not need to do any numerical approximation training or whatever. And then we try to approximate that. And then through, there are theorems that prove that when we are in forward mode, then we try to learn the solution of differential equations. We have essentially three components there. So one component is the mean square error on the residual of the differential equation, what is also called loss function. Then you have an error on how far you go from the initial and or boundary condition, and that one is the classic error you have when you don't just deal with data, because as we say in the previous episode, those are treated as just normal data. And also you have an error that takes into account the choice of where you try, the choice you made on the point you want to learn the equation. So, let's say we deal with a time-dependent three-dimensional or differential equation, then we need to pick some points in time, x, y, and z if we talk about space dimension. And that one is what is called quadrature error, because that one depends on the choice of so this point can be picked randomly, and if they're picked randomly, the error is something. If we chose, let's say, a Gauss's quadrature scheme, the error has something else, and so on. So that one is
good. So let's say that if I get it correctly, you on one side abandon the strict search for the uniqueness of the solution, because you already said my boundary condition are more like guidelines than something I really want to exactly validate, right? So in this error, there will be an error in which PINNs will not be strictly enforcing boundary condition, but more weakly enforcing boundary conditions. And then from what you say, this quadrature error looks to me a lot like what in classical FEMs is the error associated with the mesh that you have. So how do you partition your domain? You sample the points. And in that case, with standard finite volumes element theories, there you have theorems that basically ensure you that the smaller you make your mesh, the closer your approximation of this finite of this finite functional space to the actual solution is smoothly converging. And if I understand correctly, in PINNs you don't really have insurance of that one yet, but you're trying to kind of validate this error of I want to show you that I'm aware that how I mesh my domain will result in an error. Does this make more sense?
Yes, and it is kind of in there because in these these components that you have when you bound the generalization error, you kind of capture that. It's kind of that is encoded. Indeed, you see, and again, this one I have this paper under review, but when it comes out, we can actually analyze that on a simple ODE because it's very easy to see. And therefore, you will see exactly that. Of course, the bigger is your domain. Let's say you just want to solve an initial value problem. The bigger is your computation domain. Of course, the greater is the bound, and also it also depends on how much training point you are going to put in the bound. If that number, of course, tends to, let's call it n, and tends to infinite, of course, you're closer to what can be the reality, which is a continuum. And of course, if that one goes to infinite, then the error is made in a way that goes to zero. So because you
and this is actually bringing me to another of the questions of the pushback against PINNs, but just on the understanding. If I look at that as an alternative to finite elements methods, right? So if you look at PINNs in this way, and as you said, that they don't need to be just this thing, but if I look at this, one of the things that you normally do as a quality check of that kind of finite element simulation is that you take your spatial discretization that, as we said, for your PINNs will be part of the input, right? In the way you create your input, and you perform refinement studies. This is something that normally simulation engineers hate because it involves an extremely hard. So you can use your same machinery, right? But just the computational costs increase because your metrics that you're solving becomes bigger, right? And so there's a lot of time spent. But this is kind of a standard procedure when you run a simulation that has solving a equation over a mesh to discretize your domain. This is something that you kind of have to do, right? It's as important as the validation against experimental data, or even more important, one could argue. One of the problems that I see is that these, even though you're accounting for this error in this quadrature, this becomes very difficult to do in a neural network because you have to basically reforge the input, right? You cannot use, let's say you have a line that is your domain and you want to solve there, and you have 10 points of discretization. And now you want to have the same line with 100 points of discretization. For FEM, that's kind of, okay, your matrix is bigger, but you can just rerun the same thing. It's going to take more time. For PINNs, you have to reforge the input, right? From what I understand on that one. And so this kind of convergence study per discretization look way more complicated. Is it something that you normally do? Or is there a transfer somehow of a PINN that has a coarser input?
If I see your point, so there in PINNs, usually what you do, and that's what I like, that's like let's say a good point, good for PINN, kind of like bad for FEM, or like a classical method, because let's say with PINNs, say when we have 10 points, we do a training with 10 points, right? And then we do a training with 10 training points, and we get our bound, which is the order of 10 to the -1, which we all know that is not safe enough, because it's true, maybe in there our generalization error is of e to the negative 16, but who guarantees us that? The only guarantees we have is that it cannot go above 10 to the negative 1. Therefore, as an engineer, I don't trust it. Then what I do, let's say, a retraining. Okay, so let's say, okay, with 10 points, it's kind of suck. Let's try 100. Then I do with 100 point, and then with 100 point, I get the bound 10 to the negative 3. Then, okay, that's
but the 100 point is still your input discretization, right? So doing 100 point technically means that you change the network, at least the input layer of the network.
The input layer, yeah.
And likely also another couple of layers, right? Because you likely have to do some embedding on simulator.
Not necessary. No. If you just use a classic deep network, no, you just add some points in the initial layer and that's it. You don't necessarily need to do that.
So the body, let's say the body after the input layer, you keep it constant independently of how many points you give to the input. Okay, I wouldn't expect that one.
Whatever happened in the middle, let's say whatever happened in the middle, I mean, those are what we call, what at least I used to call hyperparameters. And that one are kind of like not really correlated. I mean, they can go independently. And indeed, like in one of our work, we did because we proposed like a physics-informed neural network framework with some differences, let's say a particular algorithm, and that we also did like a sensitivity analysis against the hyperparameters. That one kind of goes not like the number of layers, the choice of the activation function, and so on. So those kind of like, I mean.
So the way you try to refine is I just change the input layer, and then basically the input layer and the weights that map the input to the first body layer, right? But that's the only thing you change. You don't change actually anything else of the network. And that's a standard way in which you do that.
It's up to you. Like for instance, usually, because I give you an example with 10 points, and then of course with 10 points, if you keep in mind, and again, when my paper will go out, we can go and see the formula actually and reason on that. But let's say when you have 10 points, then it's very low. It's expected that bound is high because of that term. Then if you get to 100 points, that term goes down. And therefore, let's say still with 100 points, you're still not satisfied because maybe, I don't know, you get 10 to the negative 2, which still is fine, but we want to play safe. So you want it down to 10 to negative 3. Therefore, what you did, 100 points, bring me down to the negative 2. Well, maybe I add another layer in the middle, or maybe I change, let's say, an activation function or something. It really is up to you, like
that's the thing, because on one side, if you just change the input, that would be like great, because it's just changing one single layer, and so you keep the rest of the network kind of the same, and so you could see it like a convergence study in that sense. But I have the issue of if my network was originally built to understand a discretization of 10 points, and then I give him 10,000, likely is going to be underbuilt for getting all the kind of structures, because again, discretization of the domain is your ability, your refinement at which the scale at which you look at your physics, right? So if you want to get very small vortexes, for example in a fluid flow, you will need to have a small discretization just to be able to say I understand what happens at this scale, right? So you will never, if you have a discretization too big. And so that was the idea. And on the other side, but then maybe, you know what, that's maybe something that is good to explore with an even more complex example. I think the one you brought today is really good, but really doesn't touch about the mesh, and then we converge into the mesh problem. But maybe we can open in our next episode another thing. But because that will be my first criticism, right? So either you don't know how to refine, or you just refine in this way that is just input, or you're actually completely changing the network, and that for me looks like you're changing so many of the variables that then the two things, the two performances are completely unrelated almost, right? So it's like, okay, this network behaves like this one, and you don't have this fine control of the accuracy. But that's, I think, something extremely interesting to dive a little bit deep. It's exciting the fact that you have a new paper coming out on this one. So maybe we could use the examples when this paper is finally published. So if people that listen are between your reviewer, please accept this paper so we can finally talk about it, please. Okay, it's in the name of this podcast. But I really liked it today. So I really liked the sample you brought that I think for a good reason became one of the big example of how pins are normally introduced. But I think pins have a much bigger ecosystem behind them, and I think we started scratching something interesting on domain discretization. That is honestly one of the biggest limitations of finite elements, in the sense of even when you have an equation system and a way to solve and assemble the matrix that works really well, often that's where real engineers die because they cannot mesh domains that are too complex, right? And I think it's really nice to see how it looks on a PINN's point of view. And what I also liked is this different approach to error, right? Because in one side we have the absolute we know the solution exists and is unique, let's just find it. And in the other side of the purely data is, okay, we know we are not looking for the single unique solution, we are just trying to get a reasonable, good quality pattern extraction from our data, right? But we don't care about being the absolute minimum or bringing this residual to zero. Normally, your network will not have an accuracy of 100%, right? You will not completely bring the cost function to zero. And the pins tend to be really in the middle, right? Because they try to put this equation part of the cost function as to zero as possible, but they allow you to have a little bit of wiggle. And I think that's very interesting. I would also like to bring some mathematician behind to understand the deep theory, but that's maybe a more advanced level of it, right?
I have the people for that. Don't worry.
That's great. We can make a round table with some mathematician that can scream at each other for this. That sounds good.
You got a good point, and it's true. And also keep in mind, as we were saying in the first episode, SPC now consider the PINN is fairly new. I mean, let's say PINN are born in the way with the term PINN in 2019. So still they are baby, and again there are a lot of things going on, and and it really depends also from application to application, as I say, what we did when we started. Okay, we have this framework, which is still a PINN framework, and then we started, tackling, simplest problem, this one works. Then let's go to the next. Same, let's say, architecture works for this. Yes, no. If yes, good. If no, how can we change it and make it work, and so on. So it's really and also in parallel of that, we were trying to, try to build some theory behind it to at least, bound the error and find a common way to say, okay, if this is the bound, therefore the bound is, at least my rule of thumb is when we are down to 10 to negative 3, we are generalized well. But then, of course, that will depend on the application, and also better.
It makes a big difference between theory and application. Yeah, you have to get it. Yeah, I really like it. I think this episode at least taught something to me and made me think about discretization in PINNs, and I'm more curious about knowing more. I think we touched very briefly, and maybe we can also expand in either the next one or one of the next episode about this concept of stability, right? That again is another concept that means very different things in standard machine learning and standard equation-based system, and I'm curious to see how PINNs actually deal with that one. But we will also leave it maybe to our listeners to let us know what they want to hear, and if nobody's interested in that one, I will just ask you on a private conversation to teach me. For now, thank you very much. It was really, really interesting, and looking forward to your paper getting published and getting even deeper dive into the mesh. Thank you, Rico.
Thank you, Gabriele, and looking forward for the next episode as well. Bye.
Cheers. Bye. So here was the second episode about PINNs. I hope you found it interesting. We are already working on a third one, so let us know what you would rather us focusing on. We are going to have as well another episode of Computational Careers coming up soon. Thank you so much for watching, and have a great day.